All right, so we need to go through the kinematic equations. So if you've looked at chapter or unit 1, there haven't been too many equations we've learned so far, so we're about to add in a few more. Kinematics, you'll hear me talk about that a lot throughout the year. Some of our most basic motion equations. But they're algebraic equations where they only work if the acceleration is constant. So you have to have a constant acceleration. And often your homework problems will use that word, a constant acceleration of blah, blah, blah. And then as soon as you know that, then you know you can use the kinematics. Mentioned this already, the v naught, that simply means velocity at time equals 0. And we're going to see if we can derive some of the kinematics through algebra, given a few things. Starting with, given a formula we would know about averages. If you wanted to find average velocity and you were given your two velocities, the average in this sort of time interval, you could add them up, divide by 2. Just like if you had 2 tests, you would add up the test grades, divide by 2, and that would be your average. And that's one that will be on your equation quiz 2. And we'll come back to that one in just a second. So to solve for the first kinematic equation, I'm actually going to start with our acceleration equation we've already known. And this would also be true for average acceleration if for some reason the acceleration wasn't set. But we're assuming it's a constant acceleration. Please realize that our formula for finding acceleration, even if this acceleration is constant, would make sense to still be the same formula for average acceleration. It's just, if that's the average acceleration and it's constant, well then it's always that acceleration. So I do kind of ask that on the equation quiz. It seems like I ask it twice, but they're technically different equations. But if it was a constant acceleration, yes, it would match the average acceleration equation. Anyway, so we have our change of velocity over time. If I plug in the initial time at being time 0, that would make this velocity, we would note that as v naught. And I just simply want to solve for v. So we're just rearranging this to solve for v. And that actually is our first kinematic equation. It's no different than this, just written in a different form. So of course that doesn't matter. Multiply your t to the other side.
So how do you just get rid of the v naught?
Yeah, isn't it 0, so wouldn't you just do it
No,
the time?
Just like that computer activity pulled up, the time was 0, but that doesn't mean the velocity is always going to start at 0. Like it was set at 12. So I don't know what the v naught is. It's something. It might be 0, might not be. So I have to leave it there. So I'm kind of just rearranging this so that v is on the left. So you can kind of just picture I've added the v naught to the other side. And there it is, your first kinematic equation, which, in all honesty, is the same as that acceleration equation. And you're about to write down a whole bunch of them, or maybe they're already written for you. I don't remember. Okay, so now we're going to solve for the second equation. So that was a kinematic equation. Again, the kinematic equations are the motion equations. So they're going to have your motion terms in it, like displacement, your velocities, acceleration, time, just those variables. So now let's come up with another equation, this one that's going to have displacement involved. Starting with my average velocity equation, that was displacement over time, and my average velocity equation we just wrote down, which was the sum of the velocities over 2. We're picking those 2 velocities. So I'm just going to set these equal to each other. And I'm going to go back to delta x instead of x minus x naught. Yep, I'm pretty much just moving that t to the other side. But I'm going to put the 2 in front because that's the way it's usually written. And so now we have another motion equation. What is missing from this equation that we had in the last one? What variable?
Acceleration.
Acceleration. So that's what separates out all the kinematics, is what variables you have. Too far. There we go. So write them down. You can see we just figured out 1 and 2. You notice there's 5. On the AP test they give you 3. So that's kind of helpful, but far easier if you just know the 5. All right, we just came up with the first 2 through algebra. In a moment, we're going to do it through calculus. But no, so long as you have 2 of the equations, you should be able to come up with the rest of them if you had to. But for example, like let's say you plugged equation number 1 into equation number 2. You can kind of see where that's going to actually just get you right down to equation number 3. So you'd have V naught plus, then you'd have another V naught. So you'd have 2 of them. Then you're taking a half of it. So that go away. You multiply by that t. And then, of course, you got the half, the AT, and another t. Anyway. So just be aware that you can come up with the rest of them. Again, I also noted on number 5, the squared issue. If you're doing square root, realize you can only do the square root of a positive number. But 2 times 2 is 4, just like negative 2 times negative 2 is 4. So you have to pay attention to your context there to know if you would need to add a negative sign. Now, all of these are vector equations, so direction does matter. Positive and negative signs definitely matter. If my initial velocity was to the right and if my initial velocity was to the right and my final velocity was to the left, I would have to make sure I put a negative sign on that one. So direction matters. Pay attention to your signs. Okay. So now some calculus proofs. We'll go through a few of these throughout the year. And for the moment, I really just want you to be able to follow me. Do I expect you to be able to come up on your own, like do this on your own? Would you have ever figured this out on your own? Probably not today. But hopefully by the end of the year, after we've done a few of these, we'll get good at the calculus derivations. So I'm going to construct the first and third kinematics through calculus. And I'm going to start here. I know you guys have that itty bitty slide. This might be another case where you want to do this on a piece of paper or just write really small. I think I can fit it here, but I know your slide's like that big. All right, so we know, this is given, we know the acceleration is the derivative of a velocity function. We can actually treat this dv and dt like a variable itself and sort of cross multiply the dt to the other side. And usually, if we're doing sort of differential equations like this, if you have a dt, you try to get the dt near anything that's got t's involved, and the dv near anything with v's involved. But in this case, I don't have any v's and any t's anyway. So I'm just going to cross multiply this to the other side and leave my dv there. And now I'm going to integrate both sides. Just like in algebra, what I do to one side, I've got to do to the other. I'm going to integrate here with respect to t. I'm going to integrate here, but with respect to v. So if I'm integrating with respect to t, and I don't have any t's, this is just treated as a constant. So what did you get when you had an integral of a constant? That's a derivative of a constant. You added a t. So a is some constant, so a stays, but then we'd throw in the t. Vice versa, if we were doing the derivative of that, we should get back to just a. So the derivative of at would have just been a. But what was the other little thing we had to stick on for integration?
That was like the plus 1 plus c.
The c, the constant. Because maybe there was some constant here, and I just don't know what it was, because the derivative of a constant is going to be 0, so I don't know if there was something there or not. On the other side, I'm taking the integral pretty much of nothing. Well, really there'd be like a 1 here with respect to v. It's the same thing. My constant number 1 stays, and I would tack on my variable v. Plus another constant, call it c2.
Why did you do something to the dv but not to the dt if you were integrating them to the t and the v?
What do you mean?
I mean, on the right side you did something to the dv, but you didn't do anything because you're integrating to the v. But on the other side, when you're integrating to the t, you didn't do anything to the dt, just to the a.
This just means like with respect to what variable.
Okay,
So the dt is together, dv is together, that's sort of our notation, saying I'm integrating with respect to v. There isn't a v, so it's really as if there's just a constant of 1 there. So it's basically saying I'm integrating the number 1 with respect to v. Here I'm integrating the number a, but with respect to t. Okay, so I end up here, I'm going to put my constants together. And now that clearly doesn't look like first kinematic equation. There's definitely no c's in it a moment ago. So we've got to clean this up a little bit. Now we're going to use just some of our initial information. And it's really just going to pull in a different variable. But here's something we know to be true. We know that at, here I wrote at, and then put the t. I wanted to put the t. T equals 0. We don't necessarily know what the velocity is, but how do we write it?
v naught.
V naught. So I'm going to plug this condition that I know to be true into my equation, and that will help me come up with a term for my constants. So if I plug in t equals 0, of course that goes away. The constants are still there, I don't know what they are. And at t equals 0, v is v naught. So lo and behold, my constants must be v naught. And so now I am pretty much at my first kinematic equation. All right, and now we're going to take this one. Nothing. There we go. Stick it in over here. We're going to pretty much go through the same steps to see if we can come up with another kinematic equation. So my function for v is v naught plus at. And I'm going to do the same thing I did on the other side. I'm going to split up the dx and the dt. I am multiplying it over. I'm cross-multiplying. So all of this does need to stay together. And this is good because I do have the variable t involved, and I've got the dt to that same side. So I'm going to integrate both sides. The left-hand side with respect to t, the right-hand side with respect to x. So I do have a t here, but technically like v naught is really just a what? A constant. So I'll have my v naught, integration of a constant, stick the t on, plus. Yeah, now how do we, so a is a constant, so I'm going to leave a, but how do you integrate the variable itself? You bump up the exponent, so add 1 to the exponent and divide by that exponent. So again, remember, like the opposite of derivatives. Derivatives, we dropped the exponent down and subtracted 1. Here we're going to add 1 and divide by it. And technically there's also a plus what? Good, plus another constant. On the other side, the integration of number 1 with respect to x is just x. And then again, plus another constant.
Did you already integrate the dt on the outside?
This is notation telling me to integrate what's in front of it. You'll get used to that. So same here, this dx is just telling me to integrate with respect to the variable x. All right, so cleaning this up just a little bit, I'm just going to move my constant over, and I'm going to make that a half. Okay, so that one's kind of long, but I'd really like to figure out what my constants should be to find them. So I'm going to use the same initial condition I did over here, except instead of saying something about v, let me say something about x, yeah. Another color. How about orange? Okay. So at t equals 0, x would be defined as x naught. And if I go ahead and plug in t equals 0, of course that goes away. That goes away. So my constant is just simply equal to x naught. And I wish I had written just a little bit smaller. But, so plug in the C1 minus C2, just plug in your x naught. Yeah, because if you are looking for the third kinematic equation, which was that one on our list, the slide before, they didn't list the x or the x naught separately. Some textbooks actually do, but they combine them as displacement. So I'm going to actually subtract x naught from each side, and I know that x minus x naught is displacement. And ta-da, you've got your third kinematic equation. I don't really like regurgitation, the many forms of regurgitation, but being able to work through these steps might be something you see on your first test. Okay, so let's do page 21 real quick. Okay, and then it says, checkpoint 5, the following equations give a position of a particle in 4 situations. To which of these situations do the equations of table 2.1 apply? Meaning the kinematics. To which of these situations do the kinematics apply? And remember that we said the kinematics only apply if acceleration is what? Constant. Okay, these are algebraic equations. They have a set constant acceleration. So how do we look at these functions and tell if our acceleration is constant? So they're position functions. How would you ultimately get acceleration from them? Two derivatives. Okay, so the first derivative would be velocity, and then the second derivative would be acceleration. So I can't have t left at all in the second derivative. Can you just kind of look at them and tell in which case the t is going to go away? Number one would definitely have a constant acceleration. There'd be no more t by the time we got to acceleration.
Number 2 is the only one without constant acceleration.
Which one? Number 2 does not have constant acceleration. You're right there. 1 does. 2 does not have constant acceleration. What about 3? Is that constant acceleration or no? No. And I usually like writing those as like t to the negative 2. But you just, yeah.
So then you add 1 and it's your negative 1. So
Yeah. But 4, what about 4? You got 5t squared. The first derivative of that's going to be 10t. What's the derivative of 10t? 10. So 1 and 4 are okay. They would work. All right, here's a problem with the kinematics. So you got that whole list 2 slides ago. It says a train is traveling down a straight track at 20 meters per second when the engineer sees a fallen tree and applies the brakes. This results in an acceleration of -1 meters per second squared as long as the train is in motion. If the tree is 150 meters away, will the engineer stop before hitting the tree? Kinematics problems, I like jotting down the given information and then sort of picking through the equations I would want to use. Because in all the equations you have, there's always one variable missing, so you just got to pick the appropriate one. So we know something is 20 meters per second, but we got to be specific. What is it that is 20 meters per second? Okay, and which velocity? Correct. So our initial velocity is v0, and it's 20 meters per second. We have an acceleration of -1. So that's our A. And now here's where we kind of have to decide how we want to approach the problem. We got 2 last pieces of information. The tree is 150 meters away, and we need the train to stop. So how do you want to go about thinking about this problem? Like any ideas? What would be a good plan of attack here? What do we even want to solve for to decide if the tree is hit or not? Here's all our motion variables. You got velocity, initial velocity, time, acceleration, or displacement. These are really the only things we can solve for here using the kinematics. Okay, good. They give you a displacement, but this isn't really of the train. That's just where the tree is. So if we solve for the train's displacement, that's our question. We'll just compare it to 150 and see. But I always need 3 variables to use the kinematic. So what is that? Nope. Velocity, just not the initial velocity, the last velocity. All right, so now I've got my list of variables. I look at all these, I go back to my kinematic equations, and I pick the kinematic equation that has every single one of these variables. which the one that's missing is time. Sometimes that's easier to think about which kinematic doesn't have time in it. The last one, the squared one. And after that, it's pretty much just plug and chug. You'd of course want to make sure your units match, but they do. So we should be good. I'll erase you. So do we make it? No, we hit the tree. If we were going to slow down at that rate, we would only stop at 200 meters. And follow your signs. Acceleration was negative, so we had to plug in a negative acceleration here. Of course, that canceled out. It wouldn't make sense if we ended up with a negative displacement. All right, moving on. So since we were talking about constant accelerations, now is a good time to talk about gravity. Gravity makes things got it. Gravity makes things fall. And you hopefully remember from physical science the value of gravity. Although I left off the 1. I really like it as 9.81. Add that in. You'll get used to that. Hey, did you make our sign?
Yes.
Yeah.
My sister was the one that put it up, and I put it up there with a negative sign. And she completely messed up the test because she did all the gravity in negative. That's what the sign said.
In our textbook, it will refer to G as simply the magnitude of gravity, which would be 9.81 meters per second squared. If you want to say that's down, then you need to stick on a negative sign. Any problem that pertains to gravity, if they say something's falling, they don't need to say in the problem that gravity is specifically negative 9.81 meters per second squared. You should just know to use that value. Also, like we went over in 9th grade, if something's falling and it's dropped. Another key word there, dropped, you would know that the initial velocity is 0. It's immediately going to start to gain speed and go faster and faster and faster, but at least the very initial velocity was 0. Sorry.
So should we write B naught?
Sure. All right. Projectile motion will be more of our next unit, and it deals with kinematics as well. But just a few brief comments on projectile motion. If we talk about something fired straight up, so we're not talking about two-dimensional motion just yet, just something straight up, straight down. What's the velocity at the peak? 0. It goes up, it's about to come back down. I had to stop for an instant. If it takes a projectile 5 seconds to reach the peak, how long will it take to come back down? 5 seconds. Symmetrical. We're also going to ignore air here. And the initial velocity up, at least the magnitude of that velocity, would equal the velocity down at that same level. So if this ball were released here at 10 meters per second up, what's its velocity right there? 10 meters per second down. Okay, that will help you, I think, with a couple problems. Okay, last page. Let's do page 24 first. Okay, it says in sample problem 2-11, which it says a pitcher tosses a baseball straight up with initial speed of 12 meters per second. So we're tossing a ball up. What is the sign of the ball's displacement during its ascent on the way up? What's the definition of displacement? Final minus initial position. If the final position is higher than the initial position, final minus initial would have to give you a positive value. Maybe it went from 0 up to 10, so displacement would be 10 minus 0. That'd be positive. That should make sense. So anything going up would have positive displacement. What about something going down? Is during its descent? Negative. Because final position there might be 0, but initial might have been 10. 0 minus 10, minus 10. What's the ball's acceleration at its highest point? Careful.
Negative 9.81.
Very good. You weren't tricked. The velocity at the highest point would be 0, but the acceleration is the same no matter what point I pick. It's always negative 9.81, constant acceleration. All right, and our last example problem. I like to draw this one. I'm very good at this. A daring ranch hand sitting in a tree. Okay, hold on. Let me get my tree. All right, colors. Tree branch. He's wearing blue jeans. And a blue shirt, and he has a blue head. Okay.
What are you drawing?
I'm drawing a daring ranch hand.
A daring ranch hand. And there's a tree right there? Okay, so why does the tree have like a little incision into it?
That's a branch.
How do we know the red hand is daring?
Oh, this, you know. Because of his devious eyebrows. Okay, he's sitting on a tree limb. He wishes to drop vertically onto a horse galloping under a tree. Okay, so.
Yeah.
Is that a cat?
I was really shooting for a horse there, but. That's the saddle on the cat.
I'll
Okay.
give you a cougar. That's the best I can give you.
Is it what?
A cougar. A big cat.
Oh, okay. I'll accept that. All right, the speed of the horse is 10 meters per second, and the distance from the limb vertically down to the saddle is 3 meters. So like from here just to here is 3 meters. And the horse is going 10 meters per second. Okay, question A, how long is he in the air? All right, well, how long is he in the air? This is a question that's going to relate to gravity. So gravity is an acceleration. So I know I definitely want some kinematics involved from dealing with acceleration. So let's list anything we know about the fall. So this is only vertical information. This horse has nothing to do with this part. Okay, so the acceleration is good, negative 9.81 meters per second squared. We know he's going to drop 3 meters. I'll call it delta y instead of delta x. Do I write that as 3 meters? Think about the checkpoint that we just did. Good, he's going down 3 meters. Negative 3 meters. He's dropping. Let's say drop.
Velocity is 0.
Good. Is initial velocity 0?
Velocity not.
And how long is c in the air? So I'm looking for t. So I look at my variable list, and I find the kinematic that's got all that stuff in it. What I'm missing would be final velocity. So I need a kinematic that doesn't have final velocity. It should be.
You said we're looking for T.
Yeah.
Excuse me. Looking for t, which isn't 0.
Yes.
But we do need an equation with all these variables.
Would you use the square function? Yeah, you use the square function.
Go ahead. I thought you put it up.
You don't have time. You agree, oh, yeah, you're solving for time.
Yeah. Now, it doesn't, just because you want to find time doesn't mean it has to be an equation that says t equals whatever. It just has to be in there somewhere. We have to do the work and rearrange it. By which I mean, one of you guys tell me what that is really quick. V naught is 0, so that part just goes away. So, and I got to finish with a square root. Should be a fraction of a second. Quick fall.
Yeah.
What do you got? Anyone got a time?
Is it?
0.78?
Yes, that sounds familiar. 7.8?
What's the next one?
I'm sticking with 0.78. Okay. Store that number for a moment. Wait. Wait. Last part.
Yeah.
478 T or T squared?
That should be t, I think.
T, yeah.
So that's a point.
It was like 6 something.
Horizontal distance, there is no acceleration. Now, horse is just at a set 10 meters per second. It's not accelerating. So I don't need the kinematics if it's not accelerating. Just go back to your basic velocity as displacement over time, where you've got 10 equals delta x over that 0.78, delta x 7.8. So the horse must be 7.8 meters away to start, or else none of this is going to work out. Okay, you do have a homework quiz next time. The end. Sorry I cost you a minute.